virus.
Well, and then I just kind of patched them together. I have my own kind of notes that kind of
Let's go. You
make the transition more seamless, but I found some.
How often do you
use?
Yeah, thank you. Every couple of weeks.
Every couple.
Okay, let's get
Special day.
started. It's my pleasure to introduce today's speaker, Benjamin McKenna from Georgia Tech. He joined Georgia Tech a year and a half ago as assistant professor. He'll be talking about the injective norm of random tensors.
This is a Google.
All right, great. Thank you, EJ, for the introduction. Thanks to organizers for having me. It's good to be here. It's also good to be back at Blackboards. I work in a place with whiteboards now, so sorry if I'm a little out of practice with this. So let me, good. So the title of the talk is injective norms of random tensors. It's big enough in the back. Are you good? And everything I'm telling you about is joint work with Stéphane Dartois. Okay, so there's a couple different ways I could motivate this, and I actually want to go through quantum information theory. I'm not a quantum information theorist, so I'm going to turn this into probability very soon, I promise. So let me start talking about motivations. And what I'm going to call the goal for the talk is to answer the question, how entangled is a random, like here, random quantum state. Okay, so the reason I wanted to introduce it like this is, even if you're not a physicist, which I'm not, I think entangled and quantum should make this sound like an interesting question. That's the hope. And what I want to do in the next 15 minutes is take this sentence and kind of replace words one at a time until I end up with a sentence which is about probability. And by the time it's a sentence about probability, it's going to be about the injective norms of random tensors. Okay, so that's the plan. But I'll keep in the physics language for one more moment, which is just to say that what do I mean by entangled? So i.e., what I'm going to say is how close is a random quantum state which for me is, I'll write bracket notation very briefly. This is going to be an element of C to the D tensor with itself p times to being what the physicists would call separable. And I will just call rank 1, i.e., is in bracket notation this thing approximately equal to what I'll write as phi 1 comma up to phi p, which for me just means phi 1 tensor phi p. Okay, so if you're not familiar with, if you don't use bracket notation every day, which I still don't, despite my physicist collaborator trying to get me to do it, we're just working in a tensor product, right? And so I have these sort of pure tensors, and then I have linear combinations of them. And my question is just, is my element of my tensor space close to being a pure tensor? That's really my question. And these kind of pure tensors, I'm going to call not entangled. So just a I always mix up qualitative and quantitative. Qualitative definition of being entangled is just I'm not a pure tensor. And you can imagine there's lots of ways of quantifying that, and that's what we're going to do in the course of this talk. Okay, good. I want to say it first.
Excuse me, what's the notation before that? What separable, blah, blah?
Separable rank 1, i.e. the bracket psi is, so I'm going to write bracket with commas as a shorthand for this tensor product. But I'm going to stop using this notation in a minute or so.
And what would P be here?
How do you mean?
The number of times you're taking the tensor product.
So you can, for the most, I mean, later I'll be interested in questions of scaling limits. For the most part of the talk, you can just think about P equals 3 if you like.
Okay.
But sometimes I'll be interested actually in P tending to infinity. Yeah, so in certain communities, you're interested in P fixed and D tending to infinity, and certain communities you're interested in the opposite. Good, okay. And so the main theorem of the talk is a lower bound on the entanglement. Let's just submit it by site here. For one formalization of this question. And kind of informally, the result ends up saying that random quantum states are almost maximally entangled. In other words, they're almost as far as possible from being rank one. This, if you think about this coming from like a random matrix perspective, this is just telling me that if I take like Gaussian entries in my matrix, I'm typically full rank, not rank one. This is kind of a tensor analog of that sort of statement. And the reason this is interesting, over here, it's interesting because I'm going to tell you about two methods to answer this kind of question, which are often, or in many cases, tighter than previous methods. And the second reason is that we get constants, say leading order constants, are conjecturally tight. And I'll talk about why we are interested in this more later, but you should think, there it is, that this is sort of analogous to in the random matrix case, if this is motivation you've seen more. If I look at like the largest eigenvalue of a GOE matrix, it's sort of like we're saying this is at most 2 versus prior results largely saying that this object is big O. So it's kind of like the tensor analog of this sort of statement. Okay, good. Want to stay here. Okay. Here's your guys. So I promised that I would replace words in this sentence. I guess that the only one I've replaced so far is I've replaced entangled with not rank 1. I need to replace more words. So I'm going to replace random quantum state. What is this? Okay, so how to formalize? So maybe step 1 is I just replace quantum state with tensor. This is really kind of a semantic difference or a psychological difference more. But all I'm really saying is that I'm going to basically forget bracket notation. And I'm just going to think of T being in often CD tensor P. So now I'm just going to think of this maybe not as being quantum anymore, but just as being like a box with numbers in it. This is how I prefer to think about things often. And the one caveat I will tell you here is that in quantum information, states are normalized. So they always have unit Frobenius norms. T Frobenius squared is a sum T I1 IP squared I1 IP going from 1 up to D is 1. Okay, so I'm interested in tensors, and often I can just take a tensor and divide it by its Frobenius norm to get something normalized, and this will turn out to interact with the thing we care about kind of trivially. But this will come up in a minute. But what's nice about this now is this means that I can think of tensors or quantum states if you want. So i.e. T is the point on the unit sphere, basically. So I can now draw a cartoon, and I'm going to use this cartoon to answer kind of my second question, so step 2, which is I'm going to replace close to rank 1, or in not entangled, whatever, with injective norm. Okay, good. So I'm going to start with the matrix case here. And in the matrix case, since it's normalized, a rank 1 matrix is T just being X by transpose, where X and Y are vectors of norm 1. And so if I think about T as being a dot here, then for a general matrix, I can ask how close is my matrix to being rank 1, right? And I think if you ask like someone who's just finished linear algebra class this, the answer should be, well, I'm close to rank 1 if I have small rank, right? If I have rank 2, that's like a low rank matrix that's kind of close to being rank 1. But a different perspective is, well, if I take a rank 1 matrix and I add like epsilon times a full rank matrix, that's full rank, but in some respects, it's like close to a rank 1 matrix if epsilon is small. And so what I can think about here is I can think of the space of rank 1 matrices, if everything is normalized, as being some kind of manifold on this unit sphere of normalized matrices if I want. And then I can just ask for like a geometric distance, right? So I can say, how close is T to being rank 1? And because I'm on the sphere over here, because I'm on the sphere, a geometric notion of close to rank 1 is I can just look at the maximum overlap with rank 1 matrices, since an overlap is a good kind of proxy for distance on the sphere. So I can just look at maximum over X and Y of norm 1 of, let's say, the Frobenius inner product of T with XY transpose. Okay. So the point of this discussion was just to say that this object is maybe a plausible kind of geometric notion of how close T is to being rank 1. Okay, good. So I can rearrange this. If I rearrange this, I get the same as maximum of, I guess, Y Tx, and actually this is just the operator norm of T. Okay, so this is actually not a way I was thinking when I started this project, but this is a great fact that if I have unit Frobenius norm, the operator norm is telling me how close I am to being a rank 1 matrix in some geometric sense, which is different from just counting rank. Good. But what's nice is that now that I have this, so I can rewrite this, this is maximum over X and Y of norm 1. In components, I'll write it some ij from 1 up to d, Tij, xi, yj. And now if I look at this and I want to replace this with a tensor, so then I have Tijk, then there's kind of an obvious generalization to tensors, which is, I guess for Tijk, I would put xi, yj, zk. And that's what I'll call the injective norm. Okay, so if I generalize this to tensors, I end up with kind of the main object of the talk, which is the injective norm of a tensor T is a maximum over, in general, x1 up to xp, so I'll have 2 norm 1 of the sum I1 IP going from 1 up to D, Ti1 IP x1 I1 x P I1. Okay, good. Questions so far? live in whiteboard places, I forget about the black pants problem. Okay, so physicists realized this a long time ago, and they took this object and they defined the geometric measure, what they call the geometric measure of entanglement, which for them is just minus, okay, they like to do log base 2 of the injective norm of T as long as I have unit Frobenius norm. And the reason I need to do something like this is having a large injective norm means I'm close to being rank 1, which means I'm less entangled. So if I want to have entanglement, I need to flip the sign somewhere. And they like to flip the sign with this minus log. You can do other things, but this is what they prefer to do. Okay. So now I can take my original question, which was how entangled is a random quantum state, and replace it with what is the injective norm of a random tensor. Yeah.
I guess somewhat confusing one. So when you say close to rank 1,
Mhm.
if T is rank 1, shouldn't this be equal to 0 or?
Yeah, so I need to sort of, I guess, are you saying you prefer for this to be far from rank 1?
Maybe.
Yeah. So I guess I'm being sort of informal about that. I apologize. I guess they flip it with this minus log.
Okay. So it's not a 0 when T is a.
Correct. Yes.
Okay.
Yeah. Sorry. So this is I should be more precise, but close to far from rank 1. I guess maybe what I should say precisely is this object is measuring the distance in some respects if I flip it appropriately from the set of rank 1. Yeah. Thank you. Good. Okay. So that was kind of the motivation coming from quantum information. I'll just mention in one sentence, one other motivation is coming from spin glasses. The reason I mention this is just that I'm going to talk about different scaling limits in a minute, and some of them are kind of well motivated from the quantum side, some of them are well motivated from the spin glass side. So I'm going to at least have said that. There's a remark. I can also think of the injective norm of T as the ground state of what people would call a spherical multi-species spin glass. The argument here being, I have it up here, if I cover the superscripts here, then you might recognize, if you've seen this, the spherical p-spin model. And so once I put these back, it's what I call multi-species. If this is familiar to you, that's fine. If not, I'm just going to point to things later and say, we want to do this because of spin glasses, and I'll ask you to just trust me. Good. Okay. So having set this up, there's kind of many choices that I could make from here. Okay. So one is, for example, I can take the entries of T to be either real or complex. I'm sort of telling you, I've been a bit purposefully vague about what exact model of random tensor am I taking, and now I want to be a little more precise about this. The complex thing is the only thing that kind of makes sense from the quantum case, or the quantum side. But the case of real entries is really the classic thing in spin glasses. Okay, so both these are kind of interesting. Another choice I can make is this here. Another choice I can make is talk about symmetry classes. So I can take T to be symmetric, which means that Ti1 IP is, I can commute all the indices pi IP for all permutations pi. Right, so like T, the 1, 2, 3 entry is the same as the 2, 3, 1 entry and all this sort of stuff. Or I can just take the classic like T asymmetric, and it's actually just a big box of many different numbers. From the physics perspective, this is telling me about different kind of, for physical systems with different sorts of symmetries. This is one choice. What else can I do? Let me see. I want to say anything close. Good, okay. I can talk about different scaling limits. And I'll come up here for this. So I could take, this is Ken's question earlier, I can take P fixed, D tending to infinity. I can take D fixed and P tending to infinity, or I can just ask for non-asymptotic results. And here I should say that the case of P fixed is the classical one in spin glasses. Right, if you've seen the P-spin model, this is the same P. This is the more interesting thing from the case of quantum information. Because in this case, for example, D equals 2 is telling me about qubits. And P is like, I have a physical system with P interacting subsystems. And so they're interested in what happens if I have a very large number of interacting subsystems in my system. Okay, so I'll be interested in all of these things. You can already see that I'm going to end up with theorems of many different subcases as you make different choices here. And the last thing, maybe I will leave, actually maybe I should leave this definition up, should be good. The last kind of choice I can make is, of course, what kind of randomness do I take? So 4 is the randomness in T, and kind of the easiest thing in the asymmetric case. I mean, there's many different models, but for the moment, I guess the simplest thing is to just take the entries IP just to the IID, let's say that they're centered, and I'll give you results later that are normalized for get unit variance. I guess the simplest symmetric thing I can do is just to take T as above and average over different permutations. So to take, I guess, 1 over P factorial, sum over pi in the symmetric group on P letters, T pi, we're just asked by just permuting all the indices. Okay, so we'll talk mostly about these two models. You can imagine much more complicated things later on. But this is sort of the basic thing you could start with. Okay. I should clarify. Once I've done this, I don't have unit norm, right? So I have to resolve this somehow. And I'm going to normalize it, but the normalization process is not particularly interesting. Because then what happens when I normalize? So for example, I would take T tilde I1 IP to be T I1 IP divided by gamma, where gamma squared is just the Frobenius norm. So I1 IP, T I1 IP squared. If I do this, and because I left this definition up, you can see that everything just rescales. So the injective norm of T tilde is just going to be the injective norm of T divided by gamma. And actually gamma here is almost deterministic, right? Because it's the sum of, well, I guess in the asymmetric case, it's easier to see. It's the sum of a very large number of independent random variables. And so, for example, it satisfies a large deviations principle from Cramer's theorem. So this is practically deterministic. And so already the difficulty of the problem is just in the unnormalized thing, which is what I'm going to talk about for most of the rest of the time. Okay. Okay, so I'm going to tell you a bit about the history of this problem. And since I want this to be a talk about methods, I'm going to call this, I guess, history of methods. Okay, so let me remark first that the case P equals 2, that's actually how I motivated this. So P equals 2 is just the case of matrices. Right? And P equals 2, in that case, what I'm looking at is the operator norm of a random matrix. This is very classical. You can go to EJ's class if you want to learn more about it. And so I'm not really going to talk about this case at all. Okay, I'm mostly interested in the case when P is at least 3. Okay, so if I want to study this thing, the kind of classical technique is epsilon nets. This is used a lot. This is common, let's say, in physics. And I could put some citations. So for this particular problem, this strategy was carried out by, among others, Gross, Flammby, and Isert, 2009, UN, Treneas, Tron, 2014, Guillaume Aubin, and Sharek in 17. And more recently, this has been getting some interest in the free probability community. So there's results of March Bodiharjo in 2024 and Afonso Bandera et al. In 2024. And you should generally think that what this method does, sorry, I wanted to leave this up, keep that there. Epsilon nets generally give the correct order, but the wrong constant. So for example, in the structures of, or sorry, in the sort of normalizations above, it would give you a result like T, the injective norm of T is at most square root of P minus 1 P log P. And the thing that I don't like is that there's this universal C here. And comparatively,
I don't think they can get P log P, P.
sorry?
The dependence on P will not be root P log P. If you use Gordon, it's P.
If you use,
Yeah.
sorry,
So like epsilon net in the sharpest form, you can do like Gaussian process comparison.
Mhm.
And you even sees one, they got P square root D minus 1.
oh yeah, so this, what you're telling me is, if I understand correctly.
So
like
the
you can do
root
like
P
a-
log P cannot get from the epsilon net argument, I think.
I think so this is maybe different arguments from like Slepian and stuff.
Yeah,
So
with
like-
Slepian you have P.
With Slepian you have P, yeah, for sure.
Like
Uh,
Slepian is tight when you are in the Gaussian matrix case. That's 2 root n.
Yes, correct.
But if you generalize to order P tensor, it's P
Yes.
root n.
Uh,
It's a bit far from root P log P.
wait, so with Slepian, so in my normalizations with, and I'm actually going to say this next. So I'll jump ahead to this. What's the second thing is, the Slepians, or Studikov Fernet, however you want to call it, you get a bound comparatively. The injective norm is at most P root D
Yeah,
in my
that's right.
normalizations.
Yeah.
And so what I wanted to point to is say, well, this is obviously worse. And sorry, I should clarify. This is asymptotically as P tends to infinity. And so I just want to point to this and say, well, this is clearly Slepian's isn't tight, right? Because I can get something much better in P. But as far as I understand, the epsilon net methods do actually give this. The problem is just that.
Yeah, I don't know the reference.
Okay. Yeah, no, we can talk more afterwards if you want. Yeah, so people were, I mean, physicists were interested in getting like the correct constant here. But this is what they get, and our method will end up giving that C is basically 1 plus epsilon for any epsilon comparatively. Okay, so this is fairly good in the sense of giving the correct order, but not the correct constant. Slepian's is not tight for the tensor case for P of these 3. And the other thing that you can do, which is sort of the first main theorem of the talk, is you can use kind of spin glass arguments. Okay, so I'll say at the beginning, these are only kind of Gaussian. and they're only asymptotic, you can't really effectively use them for non-asymptotic results. What did I want to say first? Okay. Good, okay. So how does this work? So I say that the injective norm is a maximum I1 IP, TI1 IP, X1 I1 XPIP. And I'm going to write this as being the maximum of, I'll just write this as a function of X1 up to XP. And so now what I'm thinking about is the maximum of, in the Gaussian case, a Gaussian process. So I want to study the maximum of a Gaussian process. I'll make as a remark, the symmetric case is easier because of this fun theorem. The citation is funny, I'll tell you in a moment. The result is that if T is symmetric, this is achieved when all the x's are the same as each other. So the symmetric case is much easier because I actually only have one underlying x that I care about. The funny story of the citation is that you can imagine that this is a sort of result that is proved millions of times in the literature. And so if you talk to people, everyone knows it as a result of somebody else. Many people know it as a result of Banach. 1937. The earliest dating that we have found papers that found is a result of Kellogg in 1928, and van der Korput and Schake in 1935. And then people know it as a result of Friedland, people know it as a result of whatever. So this is, before ChatGPT could tell you where this came from, you just had to prove it again. So you should think this, the symmetric case is much easier. And the basic kind of spin glass argument, and this is sort of the first method that I wanted to tell you about, goes like this. So you say that, okay, I'm interested in, let's say, the supremum of, let's say, f of t. I'm going to not worry about the absolute values for a minute. If this is, let's say, real and p is even, then I can achieve it without the absolute values anyway. You can put the absolute values back later. I'm going to say this supremum is the same as the infimum of u such that f of t has no critical points above level u. And if there's a cartoon of this, if f is something like this, and u is here, ft, all I'm saying is, if you look at super level sets of u, and you don't find any critical points, that means that you're above the top point of the process. As you kind of scan down, at the moment that you first pick up a critical point, that's the supremum, because everything here is like a polynomial, everything is smooth. Okay. So this is sort of a strange argument the first time you see it, but what this means, the conclusion of this, is that if we can compute this quantity, let's say I'm interested for the moment in the regime where d tends to infinity, I'll call this sigma of u, which is the limit as d tends to infinity 1 over d log expected number of critical points above u. Then from this, I can just say, well, the probability that my injective norm is above level u is the same as the probability that the number of critical points of this type is at least 1. From Markov's inequality, this is at most the expected number of such critical points, and this is basically exponential d sigma of u. And so if I plot sigma of u, which usually looks like this, here's u, here's sigma of u, usually it has something like this. Well, that says that if I take u to be here, then I'm exponentially small. And so this suggests that I should get an upper bound, which is the 0 of this function. What this tells me is that the injective norm is at most, let's say 0 of sigma of u, okay, I guess I have to have some plus epsilon or something like this. And this is something that we know how to compute. So I can compute sigma of u with something called the Katz-Rice formula. And what that does is that turns it into a random matrix problem. Okay, so this is sort of a quick overview of this method. I want to talk in more detail about the newer one. But this is a very classical method in spin glasses. And in the case that's easiest, so the case of real symmetric P fixed, you should think that symmetric is easier because of this result of Kellogg. This was done a long time ago. I mean, initially in the physics literature, just to give some references, Grisanti and Summers, 95, let's say Talagons, 2006, Oppinger, Benarus, and Cherney. Uh, 2013, and Subag 2017. So this case is essentially completely understood. And now we can talk about first kind of main result of the talk. Okay. So I guess this is section 3 if I didn't lose count. Results. So the first main theorem, which as I mentioned is joint with Dartois, is that we use Katz-Rice to give a sort of high probability upper bound for the injective norm of T from Katz-Rice for the case of non-symmetric tensors with IID Gaussian entries. We can take them to be real or complex. I can take any kind of asymptotic limit. I mentioned people are interested in either P tends to infinity or D tends to infinity. So this generalizes these kinds of results in a couple of different ways. And the reason that we liked this was that the leading constant is explicit, conjecturally tight, as far as we know, it was not previously predicted, even in the physics literature. And in certain special cases, it agrees with a couple of different things. So I'll just write them and I'll explain verbally what they are. Susakura 2024 was independent work in the physics literature at the same time. So she was very nice. We put it on the archive on the same day. Fitter Ancien and Kita 2022, these are physicists who just did some numerics to try to predict this constant. And so the analytic formula that we found is coherent with their numerics. There's work of Subag in 2023. So this is a theorem, this is a mathematician, But it's a theorem whose statement includes unproven assumptions. And so we can sort of check this. And the last thing is work Bates and Sohn in 2025, which is after our result because we talked about it with them and they were able to figure out a lower bound that matches ours in certain of the cases. Okay. So that's the first thing. The second main theorem is the second method that I promised at the beginning of the talk. Let me just add as a remark first, this kind of constant that I kept talking about is necessary to verify there's this kind of physics folklore statement that non-symmetric states are more entangled than symmetric ones. But when you normalize everything correctly, non-symmetric and symmetric states are entangled at the same order. So you actually need to compare constants in order to understand this statement. Okay, so that was main theorem 1. Main theorem 2, I'll come over here for this. Main theorem 2. This is not 2024. This is always how it goes. It was supposed to be in the archive maybe like today, but probably next week it'll be in the archive. What we do is we introduce a new technically simple method that we're calling a moment method. So I'll talk about what I mean by this in a moment. And I want to say here. And what this does is this gives an upper bound and expectation. For so tensors of a certain type. We can do, for example, so non-symmetric tensors which are either real or complex. We can also do symmetric tensors that are complex. Strangely, we can't do symmetric real tensors. Not necessarily Gaussian. And possibly non-asymptotic. And I'll give you as an example of these bounds. For example, bounds from Katz Rice. Let me take the case of R unnormalized e tends to infinity. Katz Rice tells me that the injective norm is at most 1 plus epsilon d minus 1 p log p square root with high probability. And the moment method gives me the same bound. I should say this is the Gaussian case, just for simplicity. Gives me the same bound, just an expectation. Okay. Good. I'm going to talk a little bit about what I mean by moment method for tensors. Are there any questions first?
If you have an expectation bound for Gaussian, you can upgrade it for a high probability statement.
From like Borel TIS.
Yeah.
Yeah. So yes, we can certainly do this here. At the moment, we're mostly working on writing out some kind of non-Gaussian cases. I can do this also, I get the same bound if it's a little bit better than sharp sub-Gaussian. So if it's sub-Gaussian in the specific sense that all the moments are bounded by Gaussian ones. So for example, like Rademacher. But at the moment, we were mostly interested in introducing the method, and we didn't. I mean, you can presumably take this and run with it and try to do more complicated tensors. We just wanted to do something kind of non-trivial for the first paper. Okay, good. Yes, this is a good remark. Okay. Let's see. This is number 4. What do I mean by moment method? Good. So for comparison, I want to start talking first about the moment method. For random matrices. So for simplicity, let me take M to be a complex D by D matrix, which is Hermitian. And I'm going to let U be uniform on the complex unit sphere. And what I'm going to do is I'm going to say, well, the operator norm of M to the 2K is at most the trace of M to the 2K. Right? This is like sort of the classic argument in random matrices, because I have eigenvalues. So I'll say, well, I can just replace this by adding a bunch of other non-negative stuff. That's how I get this trace. And if you want, you can think about this as being like an expectation over U of U M2K U. Okay, good. And once I have this, now I can just say, well, just from Jensen's inequality, the operator norm of my matrix is at most this thing to the 2K to the 1 over 2K. And so I end up with expectation over M and U of U M2K of U, sorry, to the 1 over 2K. And so what you always do in random matrices is you compute the right-hand side. That's potentially a complicated combinatorics exercise. And then you optimize in K, and usually to get something optimal for the top eigenvalue, you need to take K to be the order of the log of the size of the matrix. Okay, so what happens in the tensor case? If I look at a moment method for tensors, the problem with tensors that everything, compared to matrices, everything is NP hard, but there's also no canonical notion of like eigenvalues and traces in a good way, right? So I can't take, this argument started initially with saying this inequality, which is an inequality about eigenvalues. And so I have to do something else. And what I can do nevertheless you can show, for example, if T is complex and symmetric, that deterministically, the injective norm of T to the power 2K is at most D plus PK minus 1, choose PK, expectation over U, inner product of T with U tensor with itself P times to the 2K. To improve this, this appears to be new as far as we can tell, which is interesting because it's actually not that hard to show. It's like a page. And if you do this, then of course you can take the same argument. And I end up with saying that the injective norm of T is at most, what do I get? V plus PK minus 1, choose PK. I get a 1 over 2K. And then I get, same as before, expectation over T and U of T, U tensor with itself T times 2K, 1 over 2K. And now I play the same game as I did on the matrix side, which is I compute the right-hand side, and I optimize in K. And for the same reason as in random matrices, if you give me a model of a random tensor T, I can try to play this game. The question is just, can I actually compute the right-hand side effectively? And so for the first paper, we just said, okay, if I take like, sub-Gaussians is kind of like the easiest thing to do and just to get something on the board. And there's sort of similar things for, whatever else, complex non-symmetric, real non-symmetric, this sort of stuff. But it all starts with these kinds of like deterministic inequalities that are actually not that hard to show, but are based on thinking about the moment method, not as being something about traces, but as being something about projecting onto uniform random vectors.
You need to use this so-called one-garden calculus on the uniform.
No. Well, so what we need to use is we need to use the fact that I can recognize it, or I can hook up a uniform vector in the sphere by normalizing Gaussians. That's important.
You use Week's formula?
Well, yeah, so I use Wick's formula to, well, if T is Gaussian, I use Wick's formula to compute this. But it's actually just kind of a linear algebra trick about projecting onto symmetric subspaces. I can show you later, it's cool. Good. Okay. So let me summarize. I guess this is 5, I didn't use count. Summary. So I showed you 2 methods for computing the injective norm of random tensors. I talked about Katz-Rice. I talked about this moment method. There's 2 kind of conclusions from this, maybe. The conclusion from the perspective of quantum information is that many, sort of with high probability, many quantum states are near maximally entangled. From spin glasses, or from the perspective of spin glasses, what I like about this is that it gives kind of a motivation for non-classical spin glasses. The non-classical spin glass models for example, if you take a class of spin glasses, you'll spend the entire time talking about T, which has real entries, right? There's almost no theory, there's no Parisi formula for complex spin glasses, but from the quantum side, this is supernatural. And the last thing I'll leave you with is an open problem that I think is fun. This is what, I guess I'm at 6. 6. So there's some kind of obvious open problems like, can I get lower bounds, right? That's the obvious question. But one which is a little bit less obvious and I kind of like is this. So the question is, what is the most entangled quantum state? In the sense that I told you these are near maximally entangled, but being the most entangled would mean having the smallest injective norm. So let me define MDP is the infimum, is a purely deterministic problem of injective norms over tensors that have unit Frobenius. I guess this really depends on, it depends on like, there's a version for R, there's a version for C and stuff like that. Good. It's an easy lemma. Which says that MDP is at least, get the normalization correct, 1 over D to the P minus 1 over 2. However, for some values of DNP, this is known by kind of soft arguments not to be tight. And the question is, okay, if it's not tight, what actually is MDP? So kind of shockingly, this is open for some values of DNP. And I'll give you as an example. So if T is Gaussian and normalized correctly, then the injective norm of T is at most is what we show, P log P, and then the same dP minus 1 over 2. In other words, it's kind of very close to this lower bound. There's just a square root P log P on top. And so you could kind of ask, I guess one natural question from here is, could I talk about large deviations for this injective norm to be smaller than usual, right? You just sort of imagine, like, what's the probability that this is, half square root P log P over dP minus 1 over 2? And I should get some in principle rate function. And I can see, does it stop somewhere before putting 1 on top? Okay. Thanks for your time. Oh. Yeah.
So, I'm interested, say, in computing the V that achieves the.
Sorry?
Say I'm interested in computing the V that achieves the injective tensor norm, so.
This